we see some important properties of cross spectral densities. I think we studied the properties of PSD, cross spectral density, is it? Studied the properties of autocorrelation, cross spectral density, and cross correlation. Now we see the properties of cross spectral density. See, in the case of PSD, we have only one density, power spectral density. In the case of cross spectral densities, we have two, the SXY, SYX. The first property is equivalent to Sxy of omega is equivalent to Syx star of omega. It is a complex conjugate of Syx of omega. So how can you prove this? Or you can also write this as Sxy of omega is equivalent to Syx of minus omega. Because Syx star of omega is equivalent to Syx of minus omega. See, you must be familiar with the properties of the Fourier transform. I think you already studied the Fourier transform properties, and these are very simple because this and this both are the Fourier transform of Rxy of tau, Ryx of tau. So what is Syx of omega? This can be written as minus infinity to plus infinity is a Fourier transform of Ryx of tau. So this implies minus omega is equivalent to minus infinity to plus infinity. So Ryx of tau. This is e power j omega tau dt. Is it right? Simply replace omega with minus omega on both sides. Now this can be written as minus infinity to plus infinity. See, Ryx tau can be written as Rxy of minus tau. Is it right? See, here you replace tau with minus tau. Is there any change? Then you can write it as Rxy of tau e power minus j omega tau dt. Actually, here we will get minus plus infinity to minus infinity. That can be written like this. So, which is equivalent to understood this? See, here I replace this minus with plus. Again here tau with minus tau. Simply we are replacing tau with minus tau. Replace tau with minus tau. Here what we have done? Here replaced omega with minus omega. So another important property is real part of Sxy of omega and the real part of Sxy of omega are even functions of omega. are even functions of omega. See, we already know that Sxy of omega is a complex quantity. See the difference between the power spectral density and cross power spectral density. Power spectral density is real. Why? Because limit t tends to infinity, so expectation of mod x of t whole square divided by 2t. Because right hand side is always real, the left hand side is also real. But this Sxy of omega and Syx of omega, they are complex. So they have real part and the imaginary part. That is the difference. Can you prove this? So we already know that this is equivalent to minus infinity to plus infinity Rxy of tau cos omega tau minus j times is it right? So therefore, the real part of this, the real part of this is minus infinity to plus infinity Rxy of tau, so cos omega tau dt. So therefore, the real part of Sxy of omega have the even symmetry. Understood? So the real part of Sxy of omega and Syx of omega both have the even functions of omega. The imaginary part of Sxy of omega and imaginary part of Syx are odd functions of omega. Do it later. And another property is, we already know that this is equivalent to, so minus infinity to plus infinity Rxy of tau d tau. So this implies the area under cross correlation function is equivalent to similarly, we have Rxy of 0 is equivalent to 1 by 2 pi integral over minus infinity to plus infinity Sxy of omega d1. Is it clear? Actually, this property is called as the area property of the Fourier transform. I think you might have studied the area property. Area. Area property of the Fourier transform. Similarly, if you replace this with Syx, again you will get the same equations. Ryx, here Ryx, Syx.